So, number 21. Number 21 states if a Saturn V, or Saturn V actually, rocket with an Apollo spacecraft attached has a combined mass of this much, 2.9 times 10 to the 5th kilograms, and is to reach speed of this many kilometers per second, how much kinetic energy will it have? Well, kinetic energy is just 1/2 mv squared. Now we have mass in kilograms already, but it looks like here my speed is 11.2 kilometers per second, so we should really convert that into meters per second, right? So simply 1/2 times, right, 2.9 times 10 to the 5th kilograms times this is 11.2 times 10 to the 3rd, right, meters per second squared, and this is of course kilograms, right? So I guess if you work that out, you're going to get 1.8 times 10 to the 13th joules. That is pretty sick amount of energy. But I don't think people understand that. When it reaches this speed, a lot of mass is already burnt off. So it's not going to be this exact mass that's going to actually continue to have that same speed. All right, next. So that was pretty easy. Number 25E. A proton starting from rest is accelerated in a cyclotron to a final speed of 3.0 times 10 to the 6th meters per second, about 1% of the speed of light. How much work in electron volts? This is another form of energy actually. So 1 electron volt is equal to 1.609 times 10 to the negative 19th joules. It's done on a proton by electrical force of the cyclotron that accelerated it. Okay, so if you were to think about work done, right, is equal to changing kinetic energy, really, right? And since it's changing kinetic energy, it's kinetic energy final minus the kinetic energy initial. So initially, right, it starts from rest. So kinetic energy initial is 0. Therefore, 1/2, right, mv final squared is what we have. So here, 1/2 times. Now, mass of electron, you should be able to look that up, right? Or I mean a proton, you should be able to look that up. So the mass of the proton is equal to 1.67 times 10 to the negative 27th kilograms. Now, mass of an electron is 9.11 times 10 to the negative 31st kilograms. Now, you don't have to memorize that. If you need it in the test, you should be able to look that up, or I could give it to you. So, mass of the proton, 1.67 times 10 to the negative 27th, right? Times the speed is 3.0 times 10 to the 6, right? You have to square that. So this is kilograms, and this is meters per second. Right? So if you work that out, I think you get something like 7.5 times 10 to the negative 15th joules. Very small. Very small. So that is how much work is done on proton, right? So since we know 1 electron volt right? 1 electron volt is equal to 1.609 times 10 to the negative 19th joules. If you multiply that, we should be able to get something like 47 times 10 to the third electron volts, or simply, right, 47 kilo electron volts. All right. That is something else. All right. Next. All right. A single force acts on a body that moves along a straight line. A plot of velocity versus time for the body is shown here. Okay. So find the sign, plus or minus, of the work done by force on the body in each of the time interval from A to B, B to C, C to D, and D to E. Okay? So if I were to take a look at this area, this area pretty much represents the delta x. Right? Now that delta x looks like it's going in the positive direction because it's above the time axis. All right? And since acceleration is constant, right? So it's speeding up in that positive x direction. All right, so force is in the positive direction. My delta x is in the positive direction. So we must be getting a positive work done. Does that make sense? Okay. So from A to B, okay, it looks like we are getting a positive acceleration. Right? Therefore, right, positive force. And since my delta x is also positive, right, so we got positive and positive. So work is equal to F dot delta x. And since we have positive and positive, we're going to get cosine of, I'm just going to assume like, 0 degrees. Therefore, positive work. And then from B to C, it looks like I have acceleration is equal to 0. There's no acceleration. Therefore, my force is 0. But my delta x is positive. But 0 dot anything will give you 0, right? So 0 work. Then here, my delta x is still positive. So from C to D, my acceleration is negative now. Right? It's definitely slowing down. Okay. And my delta x is still positive. So if I have work is equal to F dot delta x, it is, right, F times delta x times cosine of 180. Therefore, I get negative work. Okay. And then from D to E, this looks like a negative delta x, and my acceleration is still in the negative direction, right? So from D to E, my acceleration is negative, therefore my force is negative, and my delta x is also negative. Therefore, since work is equal to F dot delta x, I have force times delta x times cosine of 0 degrees, because they're both in the negative direction. Right? Therefore, I get positive. I get positive work done in this case. Okay? Is that, it was pretty straightforward, wasn't it? All right. Let's take a look at the next one. I have 1,000 kilogram cars traveling at 60 kilometers per hour on a leveled road. Right? Now, brakes are applied long enough to reduce the car's kinetic energy by 50 kilojoules. Right? Kilojoules. That's 50,000 joules. So, what is the final speed of the car? Well, that's kind of easy, right? So here, for part A, since we're working with work is equal to change in kinetic energy, right? Now we have to convert the 60 kilometers per hour into meters per second. Right? So V is equal to 60 kilometers per hour. Must change that to meters per second. So there are 1,000 meters in 1 kilometer, and in 1 hour there are 3,600 seconds. So these cancel out, right? And that should give us my V is equal to 16.7 meters per second. So you must have MKS system when you work with joules. All right. So here, my work that I do by the brakes, what's happening is when I apply the brakes, it takes the energy away from the car. Okay. If you ever see a brake being applied to the disc of like a race car, as soon as the brake pads like squeeze the discs, the disc gets red hot. I mean, like it glows red hot. Those Formula One cars, they like glow white, like in the broad daylight. That's how much it heats up. So by heating up, it takes all that kinetic energy into thermal energy, and then it just basically dissipates throughout the universe. So when you apply this many joules, right? So you're taking that much away. So it's like 50 negative 50,000, right, joules is how much work the brake is doing. And that is equal to, right, so kinetic energy final minus the kinetic energy initial. And that is pretty much 1/2 mv final squared minus 1/2 mv initial squared. So here, negative 50,000 is equal to 1/2 times 1,000 times Vf squared minus 1/2 times, right, 1,000 times 16.7 squared. Right? So if you solve for Vf, hopefully you can do that, you get 13.4 meters per second. So you're still going pretty fast, even though you took away this much energy away from the car. Now it'd be really nice if we could sort of I guess, reuse it or reclaim it, you know. So now I guess Tesla, they use regenerative brakes. So instead of heating it up, they turned it into electricity. When they actually put brakes on it, it turns, instead of disc holding it, they try to regain energy by turning the generator, and then they gain energy back into the battery. They transfer that energy back. All right, what about part B? By how much more must the brakes reduce the kinetic energy to stop the car? Well, if we want to figure that out, work is equal to change in kinetic energy again, right? And we want to find out how much work we need to do. So here we have kinetic energy final minus the kinetic energy initial. Now, if we want to bring it to a stop, our final kinetic energy is going to be 0. Therefore, I have 0 minus 1/2 mv initial squared. But this v initial is this v right here, right, that we calculated. So the work, additional work that needs to be done is minus 1/2 times 1,000 times 13.4 squared. So the additional work that we need to do comes out to 8.99 times 10 to the 4th joules. Still got to do like 90, almost 90,000 joules of work to stop that thing. All right. Any questions? All right. Moving on. On August 10th, 1972, a large meteorite skipped across the atmosphere above western United States and Canada, much like a stone can be skipped across water. The accompanying fireball was so bright that it could be seen in the daytime sky, right? The meteorite's mass was about 4 times 10 to the 6th kilograms. Its speed was about 15 kilometers per second. Okay? You should change that into meters per second. Had it entered the atmosphere vertically, right, it would have hit the Earth's surface with amount of same speed. Calculate the meteorite's loss of kinetic energy in joules that would have been associated with the vertical impact. So if it would have came straight down, you would have seen some craters. Right? So first thing is first, let's convert this speed v into meters per second. 15 kilometers per hour, 1,000 meters, so 15 times 10 to the third meters per second. So 15,000 meters per second is ridiculous. Okay? So for part A, let's calculate the loss in kinetic energy. The loss in kinetic energy is basically change in kinetic energy. Okay? Now the change in kinetic energy is kinetic energy final minus the kinetic energy initial. Now when it comes down and hits the earth, it's going to stop, hopefully. So kinetic energy final is going to be 0. So amount of work that's going to release is negative, well, 0 minus 1/2 mv initial squared. Well, negative 1/2 times the mass, which is 4 times 10 to the 6, right, kilograms, times 15,000 meters per second squared. Well, that comes out to negative 4.5 times 10 to the 14th joules. That's a pretty sick amount, actually. All right. Part B, express the energy as a multiple of explosive energy in 1 megaton of TNT, which is 4.2 times 10 to the 15th joules. Okay, so how many megatons is that? Well, so here's part A. For part B, 4.5 times 10 to the 14th joules. If you multiply that by, right, 1 megaton, right, per 4.2 times 10 to the 15th joules. So that is equal to 0.107 megaton of TNT. Right? So it's about 10%. Well, for part C, the energy associated with the atomic bomb explosion over Hiroshima was equivalent of 13 kilotons of TNT. So how many Hiroshima bombs would have been equivalent to? Well, for part C, 0.107 megaton of TNT, and it was what? Let's convert that into how many kilotons that is. That is 1,000 kilotons per 1 megaton, right? So this megatons can cancel out. So now we have kilotons. And 1 Hiroshima, right, is equal to 13 kilotons. So now the kilotons can get canceled out. So if you work it out, you're going to get 100 divided by 13, and that's about 8.2 Hiroshima bombs. So that one meteor is equivalent to more than 8 times the atomic bomb that was dropped at Hiroshima. that would have been some significant damage. You know, matter of fact, if that came in without any kind of warning, that country would have probably thought they're getting bombed by a nuclear missile. So it could trigger a nuclear war. You know, and people were afraid of that. They, they could have actually triggered a nuclear war. Any kind of meteor, undetected meteor coming into the Earth's atmosphere can do that. All right. Hope that doesn't happen. 2020 is still not over. Still got some time to go. All right, let's take a look at page 13. A force acts on 3 kilogram particle in such a way that the position of the particle as a function of time is given to us as follows. Right? So first, let's write down what we know. So we know the mass is equal to 3 kilograms. We also know the position function, position as a function of time, and we get 3.0 t minus 4.0 t squared plus 1.0 t cubed, where x is in meters, t is in seconds. Find the work done by the force from 0 seconds to 4 seconds. Well, let's find out what's going on. We know work is equal to change in kinetic energy, which is equal to kinetic energy final minus the kinetic energy initial. And that is same as 1/2 mv final squared minus 1/2 mv initial squared. Well, we know the mass. If we could find the final velocity at 4 seconds and then initial velocity at 0 seconds, we can find this, right? So let's find, right, v at 4 and v at 0. All right. So how do we do that? Well, since we have x of t is equal to 3.0 t minus 4.0 t squared plus 1.0 t cubed, x prime of t, which is v of t, is equal to 3.0 minus 8.0 t plus 3.0 t squared. Right? So we take a derivative of this. So since v of t is equal to dx of t dt, right? So we'll go from here to here. Therefore, v of 0 seconds is equal to 3.0 minus 8.0 times 0 plus 3.0, right, times 0 squared. We get 3. Then let's find v of 4 seconds. That is 3.0, right, minus 8.0 times 4 plus 3.0 times 4 squared. Right? So if you do your math, I think you get 19 meters per second. So change in kinetic energy is equal to 1/2 times 3 times 19 squared minus 1/2 times 3 times 3 squared. So we have 528 joules. That's no change in kinetic energy. Okay. We good? All right. Yeah, this looks like a. All right, so here we go. A crate with mass of 230 kilogram hangs from an end of a 12-meter long rope. You push horizontally on the crate with varying force of F. Varying force. Okay? So this force is not constant. To move it from 4 meters to the side, right? So horizontal distance it travels is 4 meters. What is the magnitude of F where the crate is at final position? So how much force is at this location right here when it's 4 meters horizontally displaced? Now, when it moves 4 meters horizontally, there's definitely some height gained right here. So this 12 meters of rope doesn't change the length as it reaches here, but the height that it gains, we call that y. Okay? So this A, right? So we'll call this A, I guess 12 minus y, okay? And we can figure out that this here is 4 meters here. Obviously, it's not drawn to scale, right? So we could figure out what this angle theta is. And we can figure out what the A is, because that's the adjacent, okay? So theta is equal to, right, sine inverse of opposite over hypotenuse. So I think theta comes out to 19.5 degrees. We could calculate the A, I guess. Right? What is A? A, A is equal to now, right? 12 times cosine of 19.5 degrees. What is that then? What is A? So I guess 11.31 meters. That means my y is 12 minus A. Therefore, my y is equal to 12 minus 11.31. And my y is equal to, I guess, 0.69 meters. All right, I think we know. Now we figured out pretty much a lot of stuff. Okay? So what is the magnitude of F when the crate is in this final position during the crate? Okay? So here, we know here it starts at rest. You push, 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 and then when you get to this position, you stop. So this is also at rest. Okay? So let's think about all the forces that are happening at this location right here. Okay? So we could say my V initial is 0, my VF is 0, my V initial is 0. Okay? So here, obviously I have my FG, right? FG is always going to be the obvious force, right? And then there's tension, right? There's tension, right? Now this tension will have Ty, and I'm going to draw the Tx down here, okay? Same thing if I put this here or here, okay? You know that this angle here is also same angle as this, which is 19.5 degrees, right? You know Ty and Fg has to add up to 0, right? So you know Ty has to be same as your Fg. So your Ty, which is T cosine of 19.5 degrees, is equal to mg. So what's my tension? My tension then is equal to mg divided by this, which is 230 times 9.8, divide that by cosine of 19.5 degrees. Okay? So my tension comes out to, okay, 2,391.2 newtons. So that's my tension. Well, I also know that Tx has to be exact same value as my force at this location. So my Tx is equal to the force, which is T times sine of 19.5 degrees. So the force at that location, at this right here, is equal to 2,391.2 times sine of 19.5 degrees. So the force comes out to 798 newtons. Okay? Now what? Now for part B. What's the total work done? Well, you know total work done has to equal to change in kinetic energy. But we started at rest. We finished at rest. Therefore, there's no change in kinetic energy. Right? So initial velocity 0, which is also same as my final velocity. Therefore, change in kinetic energy is 0. Therefore, work total is equal to 0. how much work is being done by Fg. That is Fg dot delta y. Well, we know Fg is mg. We know delta y is this right here, right? Times cosine of 180 degrees, because my Fg is going down, my delta y is going up, so cosine of 180 degrees. Therefore, 230 times 9.8 times 0.69 times cosine of 180 is how much work is being done by Fg. That is equal to negative 1.56 times 10 to the third joules is how much work is being done by Fg. How much work is being done by the tension? Well, tension is not, is this way, that's the tension, but is this crate moving in that radial direction towards the tension? And the answer is no. This radius does not really shrink or stretch. So there's no displacement along that tension whatsoever. Therefore, my delta x along that tension direction is 0. So there's no work done by the tension. Okay? So the delta x along the radial direction is 0. So the work along the tension has to be 0. There's no displacement along that radial direction. Well, how much work is being done by the force now? Well, the force that I'm putting in here, right, this force pretty much gave this much of work done by gravity, because there's no other forces that's going to really make any kind of work done. This is the only force that did it, right? So since the net work has to be 0, work done by this and work done by this has to add up to 0. Does that make sense? Therefore, this force has done exactly the same amount as negative of this. So I guess negative, this is kind of hard to say, okay. So it has to be work done by Fg, but negative of it. Because work net has to be 0. Because of that, work done by F is equal to negative of negative 1.56 times 10 to the third joules. Therefore, work done by force is equal to positive 1.56 times 10 to the third joules. Now, I know somebody's going to ask me, But can't we just dot this and 4 meters to get that work? And the answer is no. Why not? If this force was constant force from here to all the way here, yes, then we can do that. But because this force is not the same from here to here, we cannot use that dot product. We have to, I mean, here is almost like zero. And then it's going to increase, 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 increase to 798 newtons. So we cannot use the dot product because the force is not constant. Okay? So work done by F does not equal to F dot delta X because F is not, right, constant force. F varies over delta X. Therefore, we cannot use this dot product. Okay? Very important. This is a trivial mistake people always make. Okay? All right. We're almost done. Power. All right. Power is a time rate of how much work is being done, or simply the derivative of work done with respect to time. Okay? However, if the force is constant, you can use power as F dot V as your instantaneous power. That's very important to understand. This is only true if force is constant. The loaded cab of an elevator has mass of 3.0 times 10 to the third kilograms and moves 210 meters up the shaft in 23 seconds at constant speed. So what is the average rate as the cable do work on the cab? Okay, so let's find out how much work is being done on the cab. Okay, that is F dot delta Y, basically. Well, what is my F? That's the same force as Fg, because it has to be minimum of the weight of that cab. Therefore, this is mg times delta y times, right? Well, angle of Fg, but this force has to be up because you have to, pull this much of weight force in this direction. So this is the force, right? So same amount as your Fg. So this is actually this. And since your delta y is going up, your delta y is also up, right? So this is going up. So this is cosine of 0 degrees. Therefore, right, you have 3.0 times 10 to the third times 9.8 times 210 times 1. And you get 6.174 times 10 to the 6 joules. That's how much work the cable is doing. Okay? Maybe I should do this force cable and make this force cable instead of FG. Force cable. So that should avoid confusion. So the power now is equal to, right? the rate of work done. Therefore, I got 6.174 times 10 to the 6 joules over 23 seconds. And that is 2.68 times 10 to the 5th watt. And what is the unit of power? Okay. All right, last one, 42. At a certain instance, a particle experiences a force of this much. So here's my force. And my velocity vector happens to be negative 2I hat plus 0J hat plus 4K hat. So what's the instantaneous rate at which force does work on the particle? So what they're looking for is instantaneous rate is basically, right, power. So since power is equal to F dot V, right, and we have this Cartesian form, is basically Fx times Vx plus Fy times Vy plus Fz times Vz, right? We should all know that by now. I mean, if you wanted to do like the magnitude times cosine of the angle between it, but we don't know the angle between it, so we can't really do that. So here we got 4.0 times negative 2.0, right, plus negative 2.0 times 0 plus 9.0 times 4.0. So what do we get? We get negative 8 plus 0 plus 36, right? Therefore, it is 28 watts is how much power. This power should not be vector, by the way. Sorry, I got a little carried away with the vector symbols. It should be just a scalar quantity. That's part A. All right. If the part B, at some other time, the velocity consists of only J component, if the force is unchanged, and instantaneous power happens to be negative 12 watts. Right? So for part B, power again is equal to F dot V. Power this time is negative 12. Your force vector stays the same, but your V at this point is only 0I hat plus something J hat plus 0K hat is what we have. But the force stays the same, right? The force is basically still 4.0 I hat minus 2.0 J hat plus 9.0 K hat. So everything should pretty much go to 0 except for, right, negative 2.0 times y. Because this should go to 0, this should go to 0, and this times y is the only thing that should add up to negative 12. So my y is equal to negative 12 over negative 2, which is positive 6 meters per second y hat. That's my v of y then is equal to positive 6 meters per second. Y hat is what the v of y should be. All right. All right. I'll stop here. Let's take like a 5-minute break. And before you go, 5-minute break, let's print out the test so you can let it print out. I'm going to stop the lecture here.